Hi everyone, welcome back. Today's lecture 2, energy production and exercise. First we need to look at muscle energy production. So before analysing any form of human function, a basic understanding of how the body uses that energy to produce movement is needed. Essentially we're looking at energy being defined as the capacity or ability to perform work. Without energy there would be no light or heat or anything. Everything would be stationary. Energy is fundamental to everyday living and is needed for action and change. Some examples of energy that we need in our daily lives are heat, light, sound, etc., and can be stored or potential energy. So we're looking at the difference between our kinetic energy or movement and stored or potential energy. So within our bodies it can be stored, or within food. And I guess they're the main ones that we're looking at. So energy is mainly concerned with the transfer of chemical energy into mechanical energy. Humans obtain that energy from food that we eat, and energy from food is measured in kilojoules. So essentially, to remain fit and healthy, we need to match our energy intake with our energy output. So we have to do as much exercise and burn as many kilojoules as we eat to maintain that healthy balance. The transfer of energy from chemical energy or food into mechanical energy in the human body is not direct. So instead, the energy is actually gained from the breakdown of food. So our body breaking down that food is used to make a chemical compound called adenosine triphosphate, or as you would probably more commonly know it, ATP. So a little overview of our energy systems. We have the anaerobic energy system and we have the aerobic energy system. And in this table you can see the system, the source of fuel that it uses, the duration the system will last for, what generally causes fatigue of that energy system, and the efficiency of the ATP production, so that ability to reproduce the adenosine triphosphate. So in our alactic systems, or our ATP-PC system, the source is the phosphocreatine, so the PC. It doesn't last very long, only up to 10 seconds. Depletion of PC stores is what causes that energy system to run out, and it's rapid, but it's limited, so it happens really quickly, but it won't last long. In comparison to, say, our aerobic system, where we use carbohydrates, glucose, glycogen, fats and proteins as the source of fuel, some more important than others. And it's indefinite at low intensity, so it's what we use in that day-to-day activity. Depletion of fuel sources, and when we look at aerobic system, this is the order that our body will use it. So from carbohydrates down to protein, protein being the last source of energy that we don't want to have to start to use. And the efficiency of it, or of the ATP production, is slow, but it's continual, so we can maintain that energy production. So what are they? Anaerobic energy is not using oxygen, and aerobic energy is using oxygen. In contrast to, say, just those sources of fuel, we need a system for breaking it down, whether that's using the oxygen or not using the oxygen. So what should you know about our energy systems already? There are three main systems in our body that allow us to perform sporting activities. The main source of energy is food. Foods with carbs, fats and proteins are the best foods to eat when gaining energy. That's why we tend to have high carb, high protein diets to try to, say, bulk up. The three energy systems in our bodies are that ATPC, the lactic acid and the aerobic. The ATP system is very fast energy production, which means that it's essential in allowing a 100-meter sprinter to finish their race at a high intensity. Keywords there, high intensity. Whereas the aerobic system is very slow in producing energy, allowing a marathon runner to keep running for a long period. And that lactic acid system kicks in that middle zone, so it's quite fast, but it's far better suited to a 400-meter race where someone is running at a moderate high pace. You can see in this image, and I will use a fair few images to help you understand the relationship between the three energy systems. You can pick the one that works best for you, and I'll go through them a little bit later in this lecture. But here you can see at the center we have energy, energy here being at the center of it, and it's really just how we then feed into that energy system, okay? Each for their own unique source. So a little bit more in-depth information about that energy production is looking at that adenosine triphosphate. So we're looking at the transfer of energy from chemical energy, so from food, into mechanical energy, which is action by the human body. Instead, the energy gained from the breakdown of food is used to make the chemical compound. So I went through that before. We ingest food. We use that food to help break down this chemical compound called adenosine triphosphate, or ATP, and then we use that as the mechanical energy or action for our human body. It's only when this energy is released, or by the breakdown of this compound, that it can actually be used by the body's cells. So it's really, really energy-rich chemical compound that is already found within the body. And this is what it looks like. So these three orange bricks are your adenosine, and then attached to that you have three phosphates. Now, what happens when we break down the adenosine triphosphate is we actually separate one of these phosphates here on the end and break this link. That there is what we consider creating the energy that we use. So here you can see it. The adenosine with the two phosphates plus the phosphate that was broken down equals energy. All right, now this resynthesis from adenosine diphosphate, 1,2, needs to happen in order to continue to produce more ATP. So once we resynthesize this lonely little phosphate here, then we can break it down again, reuse that phosphate. So a great deal of energy is released when this bond is broken, and this provides the energy that powers the human body. This image is from your book, from Mesros. So you can see here, again, the adenosine plus your three phosphates, which is essential for muscle contraction, nerve impulses, hormone secretion, everything that happens within your body. And when we break that down, we're able to utilize it around the body, and then we have to resynthesize that last phosphate group in order to create ATP again. And then we go back to the top where we have our adenosine triphosphate, and we can reproduce those actions again. So when we look at food for our ATP production, we know we have different food groups. Fats and simple carbohydrates is this top part of the triangle, as we know them to be unhealthy foods generally. Then we have our protein, so eggs and meats, and our complex carbohydrates, which are our slower burning nutrients for our body. We'll look at them all individually. So complex carbohydrates. When we look at the carbohydrates, we're looking at them being broken down in the body into glucose. Excuse me. The glucose is then stored in the muscles and liver as glycogen, so storing it as sugar that we can then use to break down and then reproduce ATP in the body. Simple carbohydrates, so the ones at the top of that pyramid, are the sugars. They can provide energy, but it's not a great source of energy. Complex carbohydrates we know to be a lot better as athletes. For example, 1 gram of carbohydrate yields approximately 16 kilojoules of energy when broken down. And I'll give you some more comparisons in a minute, so remember that. Food for the replenishment of ATP in terms of fats. We have 3 different types of fats within our body. We have triglycerides, we have free fatty acids, and we have other sorts of fats that are stored within the body. These are all stored in our fatty tissue or our adipose tissue, and we can use them, and our body does burn them, but generally only when we're using that aerobic system, so at that prolonged lower intensity work. The body uses that to produce the ATP and continues to break down the adipose triglycerides. We know this as, for example, going for a run to lose weight. The whole idea behind that concept is that we are using our fat stores to produce our energy source. And that way, we're starting to burn the fat. However, 1 gram of fat yields approximately 37 kilojoules of energy when broken down. So that needs to be taken into consideration as well. In other words, it takes many more chemical reactions and much more oxygen to split them and resynthesize that ATP, which as athletes, we don't want. Proteins. So we know protein is really good for exercise. However, we tend to see it more in our recovery foods when we're trying to heal muscle, as opposed to using it as an energy source. And it's really only used as an energy source, for example, in starvation mode or prolonged exercise. So a marathon runner would start to eat into their protein energy source, which isn't good. But again, it's 1 gram of protein yields approximately 17 kilojoules of energy when broken down, which is a pretty good outcome, but it's not the right kind of energy we want to produce. So where's it all stored? It's mostly stored in our muscles, so protein in our muscles and our adipose tissue. Carbohydrates stored as glucose, and it's in our blood, muscle and liver and our adipose tissue, and the same with our fatty acids and our fats. So how does this relate to energy systems? Here you can see we have our ATP system, we have our lactic acid system, and we have our aerobic system. Now, you can see how I've pictured these to nest inside of each other, basically because you tend to use this one up before going into this one, before going into this one, although that's not always necessary. And so quite often you'll be using your aerobic system and tapping into one of these systems whilst using that aerobic energy system. For example, playing soccer and going for a sprint. Here you can see again, down this end we have our ATP and our squat or our snatch, and then down this end we're purely oxygen-based energy replenishment, and we have our cross-country skier. So 2 ends of the spectrum of how we produce energy. Energy sources and the duration of work. So again, this is the third image now of what our ATP or our energy systems look like, why they're used, how they're used, and how long they're used for. So a maximum rate of energy production. You can see that ATP store, boom, 2 seconds, that's all. Our ATP-C system, so that ATP system is the quick reaction. You can use it for slightly longer in terms of a 10-second sprint. Maybe you sprint 100 meters, or maybe not that quickly, but 100 meters. And then we have our lactic acid system. You can use for around about a minute, maybe to 3 minutes, depending on how fit you are. And then everything over that, or during as well, as you see it works through that 2, 10 to 1 minute section. You can use it and use that to replenish your energy for long periods of time. Again, another visual for you, pick the one that you're most comfortable with. You can see the ATP contribution, so how much ATP it's likely to use. Phosphate, or that ATP-PC system, runs out really quickly. So it'll give you a high amount of energy at this end, and it won't last very long. So short and high, long and low, not very much usage here. Whereas your anaerobic glycolysis, we're looking short amount of energy, so small, high intensity, around to this side where it's low, but this is your peak area here in the middle where it's got medium intensity. So thinking through that middle line there. And the opposite applies to our aerobic system. You can use your energy system for a long period of time, and it'll kick in, but it's a low intensity. Again, last image for you to have a look at. This one shows you in that 100-meter to marathon race, and how long you can use that energy system for. So about 10 seconds at this point. We're starting to look at that anaerobic energy kicking in here at the lactic system. And then everything over 2 minutes, 2 minutes is 50% of each. And then we're looking 2 hours is solely aerobic, very, very little anaerobic contribution. Energy system recap, you've got your fuel, duration, case of fatigue, the byproducts created. So when we think about in terms of that lactic acid buildup, we have a negative byproduct that's created as a result of our hard work and our energy production happening at such a rapid rate. Important here as well, your recovery time takes not that long to recover, longer to recover, longer again to recover, depending on the exercise that you're doing as well. So just have a little look over that for a moment. All right, so maybe rewind, watch little bits of that again, the parts that are relevant to the way your mind thinks, and then maybe come back to this point and look at how do we evaluate. So for starters, energy systems and fitness components. So in the following table, I want you to illustrate the relationship between the fitness component and the energy system. I've done the first one for you. So fitness component would be aerobic capacity. The energy system that would be utilized would be that aerobic energy system. So have a think about it now. See if you can answer those. All right, we'll try out my ability to write on the screen here. You should have got something along the lines of ATP for this one. Again, muscular endurance, we're probably looking at that lactic acid. If you're thinking about, say, a 400-meter race, that's terrible writing, a 400-meter race where you're really depleting your energy stores and working really hard. Muscular power, ATP. There we're thinking along the lines of a jump. So jumping for a rebound maybe, or in long jump. And speed, depending on what sort of speed we're looking at, but generally ATP, because speed is essentially something that is performed at a high intensity, which we know needs to be ATP source. Hopefully you got something like that. All right, a little story for you. During most physical activities, the body uses a combination of all three energy systems, depending on the duration and the intensity of activity. Hopefully you've got that from what I've been saying so far. The example that I like to use. Soccer midfielders use the aerobic system to provide the energy required to keep moving back and forth on the field, usually at a moderate level of intensity, but they are able to continue for that long period of time. Occasionally they may need to sprint down the wing to assist in attack or defense. These short sprints usually last from 3 to 10 seconds and are fueled by that alactic system or the ATP-PC system. Because the body's stores of PC are quickly replenished, we know that they will replenish within 2 minutes. Soccer players are able to sprint many times with rests in between. That can be during lower level energy consumption, so jogging will still replenish that energy system. It's only during a series of continued sprints without any rest that a midfielder's lactic acid levels will accumulate to the point of fatigue. At that point, it tends to be towards the end of the game, and that's when we see people starting to get muscle cramps. So, an evaluating task for you. This you need to fill in your workbook, and we'll go through them in class. So I want you to prioritize which energy system is most important for the specified activity and justify your answer. So we have our 100-meter sprint, which uses that creatine phosphate or that ATP-PC. Notice PC and CP are the same thing, so phosphocreatine or creatine phosphate. The justification for that would be a 100-meter sprint requires a maximum explosive movement and is very short in duration, between 10 and 20 seconds. All right, pause here and complete this table in your OneNote. And lastly, I want to finish with the fact that it's important to understand the energy demands of different types of physical activities. Once you determine the energy needs of different sports, you can adapt your training to suit its needs. So also we need to think about those fitness components, what energy systems each of those fitness components rely on, and how can we make our training suit each of those energy needs. Okay, well done guys. That is the end of your second lecture.